Okay. Okay.
Is Christoph joining?
He's in vacation. So. I go. So can you see my screen, or do you need to increase the font? Good. Perfect. Okay. So the last time we went look at the example here. We went to see how we define actors and how actors are implemented in the framework. And we went through discussing asynchronous programming and the difference with respect to parallel programming. There's some similitude and some differences here. And the fact that all the actuators are asynchronous, meaning they can run in parallel. There's some extra precaution that you need to take to avoid that they work on each other's feet, and you have data races and things like that. So I showed you last time that that's why you need to kind of embed your the client that you pass to an actuator into some containers that Rust provide that give us additional safety on manipulating data in parallel, like ARC, as atomic reference counting box pointer, which allow to access data to get reference to data, but keep track of how many references we have about among multiple threads. Because like this, we guarantee that the data will be never removed from the memory by one thread, while another thread is still needed, for example. That's the advantage of the ARC. And we talk about the mutex. I think, went into detail that I think we're going to see today how is it used internally. But first, do you have any questions from the last time, or not yet? Okay, let's get started. Okay. So I think today we're going to focus on understanding inputs and outputs, how it is implemented, and how we define, how we create new inputs and outputs, and what kind of safety the compiler provide, thanks to the way I've implemented that. Yeah, and how we add input and output to the system. So if you remember, last time we saw that we have basically just for the simple model, we have 3 actors: a source, a logging, and a source which made with this. We have a signal client which turned into a source actor. We have our logging where we save our data, and we have that's all, I think. And we have a filter, sorry, and we have a filter which going to take the signal in, make a modification to it that it can noise, and then going and the output going to the logger. And yeah, that and so well, and yes, and here you can see that we take the source, and is how we start to connect everything. So we take a source, we take our first actor, which is generating the signal. We add an output to it, and it uses a builder pattern. So we get a builder, and then we have to build it, specifying the type of that data we're sending, and there's a type corresponding to also the unique identifier of the data we're sending. Like this, the compiler can figure out if we are sending the right data to the right place based on the unique data type we have. And then this output is sent to the filter and to the, the logger. I must have modified that because I can see that there's something. What? Something might happen. Roll out that. Example. Okay. I was locked from modifying the code for some reason. Okay. Yes. Okay. So let's see. Let's go back to the code itself and see how all that is implemented in terms of all that source actors. And so if you remember, this is like the actor structure, which, as I said last time, is relatively simple. It's a vector of inputs, and you may or may not have input, so it's why it starts with an option. A vector of outputs, again optional, and a client. In fact, it's a reference client, why it's an arc. And what you put in an arc usually cannot be mutated. But here we want to be able to modify the state of our client. So that's why there's a mutex, and we'll come back to that. And you can have optionally give a name to your actor. Okay, and so if we look at input and output, so it's defined. So you see, I have something a bit also weird here. So it's a vector of output, but if you look at the type of it's a box of DIN input object. There you go. Again, the Rust complication again here. So what is that? So to understand that, let's open the I/O module and the input implementation. Input is simpler than output. Output are relatively simple. Here is the input structure, and you see this is the input structure, but I get input object. So my vector, I say it's a vector of input, but the type is a vector of box DIN object. So there's something here that I need to explain. But if you look but really what the vector is really a vector of input. I will explain why I have to go through box DIN. So let's focus on input. So if you look at the properties, we have a receiver because an input is going to receive data from another actor, and the client, because as soon as we receive the data is going to be read by the client to update any internal variable that you will need later. So that's why, for example, that I bound. So if you look at the generic parameter of the input, there's the client, and the client is bound by a thread, which is a read thread. Remember, a client needs to have 3 threads implemented: update, read, and write. If we look at, if we go back down here, you see that actor requires the client to have the update thread implemented, because it's an actor, it's within the actor, it's from the actor, sorry, that we're going to update the state of the client, but it's from the input that we're going to read new data into the client. That makes sense? So Rust can really follow your logic. You know, we have the actors, and the actors are going to, loop, update the state of the client. So you make sure that that like this that the client is going to implement the right requirement. So otherwise, you won't do what you want. And the same for the input. The input must be read by the client. So we bound the generic parameter C. C can be any client as long as he has read implemented. That makes sense so far? So that's why we pass a reference also to the client to input. And so it's just a reference, it's just a pointer, so it's nothing very heavy to pass. Okay, so we have our input, and we have our receiver. If we look at the main function of input is really to collect data, receive data from clients. So this is the main function that we implement. I remove all the log from it because it's relatively simple. So there's two line really when you receive the data. So if we look at this part first here, it's where we call the receiver Rx. It has a receive assign function. So it's where we're going to receive the data. So the output of this function is effectively the data we are expecting from the other client. And you see the await here because they are asynchronous function. So what that means, and remember when we talk about asynchronous and the difference with parallel, is that there's a supervisor somewhere which keep track of all the thread running on. So when we have an asynchronous function like this, and we pass a wait at the end, what that means? That means that we tell the supervisor, okay, you cannot go beyond that point until this function has exited with the output you need. But if you have other threads that are awaiting for something to happen, I give you the opportunity to do something else or something in parallel, right? So you tell the supervisor, okay, at this point, you can do something else, or you can do run this function. And in a multi-threaded environment like we are, this will run in parallel with other things. But if all the CPUs are busy, then you give him the choice of moving something else that are waiting, and then coming back to that later. So so there's no kind of starving of the system by one thread which will run all the time. Here, the supervisor will distribute the load. Okay, that's why asynchronous programming is quite interesting. And then the data came out, and then we use the read function from the client to pass this data to the client, right? So this is the read. So that's why when we define input and we have our generic parameter C for the client, we put a bound to tell, okay, that he has to implement the read function. Otherwise, the compiler will say there's an error here. I don't know where read comes from because the client is a generic parameter. But if you say it's a generic parameter, but he must implement read, so the compiler will look at what are the functions in the read trait, and we say, okay, there's a read function, then it's fine. If it does it, it's okay? That's how it works. So, but to get the client, it's a little bit more complicated because you see the client is in an arc and in a mutex. So in an arc, it cannot be mutated. But because it's a mutex, when we get the value within the arc, we can apply a lock on it. And the lock means that so when you have the lock, if there's any thread, if the client has been locked by another thread, you won't get it unless there's no other lock existing. And then once it has never been locked, collected and blocked by a thread, this current thread will take the client and will own it. And if other thread will come and say, okay, I need also to have access to this client, it will just hold, just wait until this one has finished.
So it can't read it, and it also can't manipulate it, right?
No, it can't do anything. It's really kind of stall the client, and nobody can get access to it. So it's very safe in that case, this kind of references, because it ensures that if you have multiple threads that have a reference to the client, and because all these asynchronous threads that we have, at some point some will try to access the client at the same time. You won't write twice to the client in the same area, so it's very safe. They will take time. So it's asynchronous, it's in parallel, but sometimes things will happen sequentially just to avoid any memory being overwritten issues. So that's why the mutex come into play. What mutex give you? The lock function applies to the mutex. So when you have a variable within the mutex, to access it, you need to lock it first. And in Rust, you have several implementations of the mutex. I choose the one coming with the asynchronous lab runtimes I'm using, which is Tokyo. So because it is asynchronous, you have also the await function. That means, okay, to tell the supervisor, okay, I need access to this variable, so I need to be locked. So I cannot move further that line of code. But if you have anything else you want to do before locking it and giving me access to the client, please go ahead and then give it to me. So that's why we have await also here. So here we get the client. And then when we have a client, we can manipulate it with like a regular variable. That makes sense? So that's the use of the mutex. So there's a bit more step involved than when you do, because when you do a single thread, I think, application. But this extra step, when you get familiar with it, make it very, very safe. Compare, for example, if you were to do the same thing with C++, there's no guarantee like this. You need to be very careful by yourself, otherwise, and that's become very, very difficult. So this extra step adds some complication and there's an extra learning curve, I think, a step in the learning curve, but it really makes it step. Okay. So that's what the input is. Simply. So we go back. What we learned. So the input depend on the client C, which need to implement the RAID thread, and it's just simply a receiver. I will come back also explain how we get a receiver. A receiver and a client in an ARC in a mutex, and when the main functionalities of an input is to receive data and invoke the client to read the data. That's simply that. And there's some extra safety steps that we need to take to make sure that the client is accessed uniquely, as only one access to it. That's all. Okay. And then there's some back and forth also with the asynchronous supervisor, and like this we let him manage the workload among the threads. So basically, all these extra await, lock, etc. are there for that. It's to manage all the asynchronous and parallel behavior of the system. Okay. But still, I just talked about input, and I said that the actor is a vector of input, but it still looks like I'm lying because it's not a vector of input, it's a vector of something called boxed-in input object. So what's going on? Okay. So let's look at the type of the input. The input of the type of the input is would be the type of the client. And remember the data that we pass has two types, the primitive type and the UID, unique identifier type. And so and these are passed to the receiver. The receiver needs to know which data, the type of the data you're going to pass. And I also added the rate, the rate at which the input is going to be invoked. Okay. So when you are multiple inputs in an actor, the client will be the same. The rate of the inputs are the same, but T and U, the primitive data type, and especially the UID, U, will be different. So each input will have at the end a different type, because at least U will be different for each input, at least. Okay? But you cannot make a vector. Go ahead.
Could you repeat what is the T is the type? What's the C?
T is a primitive type. Let me open something else. I think maybe.
I'm not talking about the T. I'm talking about C.
C is a client.
Oh, okay.
C is a client.
So it's the client that is sending data to the other client.
So input receives the data,
okay.
And then we call the client to read this data.
Oh, okay.
Okay. The input is really the receiver. Go ahead.
I think this answers another question. In terms of organization, you have an input.rs file where you are defining the inputs for the clients to get the data.
Yes.
I'm just saying that because now I think that I understand the client. So in other words, the input definition is not something that belongs to the client. It's something that is in a higher level in the hierarchy of the computational system. Okay.
Exactly. Now the client has no input-output. The client, as I said, I think the last time, is really the physical model, and it's just that. And we add extra functionalities through traits to read and write data and to update its state. But the communication is made by the actors and the input module, with the I/O module, which have input and output. Right? So here the input just has a receiver, and once he receives data, because he has reference to the client, and because when we imposed the restriction that the client must implement the read thread, he can call the read function of the read thread on the client to pass him the data, right? Okay. Any question on that? No. So I was going back to the type of the input. Each input is going to have a different type, because at least I was saying U, which is a unique identifier of the data we're passing, is going to be different for each input. T may be different, maybe not, we don't know, and C and N are going to be the same. But if you look at the definition of a vector in Rust, you cannot have a vector of different type. All the vectors are the same type. So you cannot. But in fact, you can. There's always another way to do it. So that's what took me because I need some time to get familiar with. You can define, you can create a vector of trait. And so the vector of trait, so you just kind of pass a vector of functionalities. That's the way I like to see it. So you don't pass the vector doesn't hold data anymore. It's just a kind of what's called a fat pointer. So it's a pointer with multiple pointers inside, where you have a pointer to your original data and a pointer to some methods, because you can also have a pointer to functions. So you have you create a vector of functionalities defined in traits. That's why I have this box of DIN output. And that's for me one of the most difficult, I think, concept I met with Rust is this kind of trait, but they're called trait objects. So they are traits, but they are kind of special traits. So let's see how this is defined, and then we'll come back and making sure we understand that. That's an important concept. So this is a trait object. You see, it starts like a regular trait, cube, trait, input object, and we define, is where we define, in fact, the receive function, and then we implement here our trait for the input. So it really looks like any trait we used to do, right? So that's really a trait, and you see, so we define an input object, and and we implement this trait for the input here. Okay, a regular trait so far. So I said that in a vector you cannot pass element of different type. Okay, so if you look at the type of input object, it doesn't depend anymore on any generic parameter. It's just a type of input object. So now if you could put that in a vector, you can have a vector of that. So that's a trick that Rust allows you to do. You know, if you have a structure like we have input, which depend on generic parameter that's going to be of different type, then your inputs are going to be of different type. So you cannot put that into a vector. But so what you can do is you can create a trait which have the functionalities you want to use from the element of that vectors, and put that in the vector. And then because you kind of erase the generic type because you just do the implementation for an input with generic parameters, but the trait itself doesn't depend on that. Then you're safe and you can use that in a vector now. You see the tricks that Rust is using here? Then suddenly the vector again receives the same type and it's okay. Even if behind the scene it has implementation for different type, but the compiler doesn't see that. Does that make sense?
It's kind of like passing a vector of structures or structs or something, and in that struct there's like different types. Yeah.
Yes. Something like that. Okay. So that's why we have to do this little juggling here, where we have a vector of input object, and we have to put that into a box. Okay, that starts to be the idiosyncrasies of Rust. It's because a vector, there's also the restriction of the vector, where a vector needs to know the size of its size in memory. But input object is just a trait. It doesn't have a specific size. So, but if you put it in a box, which is a kind of a reference, which is always a pointer, then a pointer is always the same size, and then again the compiler becomes happy. So that, yeah. I think do not worry too much about that right now. It's if you read the documentation, they say it's the way to do it, and you do it that way. But now that I understand better, it's because of that. There's also the size issue in the memory. So that's why you cannot do directly box. You cannot move a vec of input object, and you need to put in the box. And the DIN really is here to make the difference between regular trait and a trait object, because you cannot put any trait into a vector. This is something that caused me a lot of trouble getting it right. For example, you can have some trait which take here as a definition some generic parameters. That's not allowed when you want to put it in a vector, because in a vector you need to know exactly you need to know all the type in advance. Otherwise, you may have different types and it doesn't work again. Right? And there's also restrictions that are a bit in play here, so you need to be careful. Okay. So that makes sense. So that shows the power of Rust, but also how much new concept you can pack in a single line. In this line inputs, we look at arc, mutex, box, head object. The DIN keyword is a lot of things. That's fine. Okay. But at the bottom line, it's a vector of input, but input of different type. And so the actor only sees the functionalities of the input defined in the trait. If, for example, we see an input, I implement the new function, the new method on input. I cannot call this new method from the actor because it's not defined in the trait. So that's also a restriction. You cannot. So you have to be careful to know in advance what functionalities of your structure you will need into the actors in that case to put that in the trait such as you have access to it. Okay. So far so good? Okay. So we see input, output is the same idea. There's also an output module in the create output module, and it's the same idea. Here is the definition of. So I have output. Where is the output? Here. The output is slightly different. That you recognize a few things. So you have a transmitter, TX. So remember, our output is to send data to other actor. So you have the transmitter, and again, you have a reference to the client in a mutex, in an arc. And the only difference the main difference so the input, we have a receiver, the output, we have a transmitter, but we have a vector transmitter because we are allowed to have the same output sent to multiple places. So that's why we have a vector of sender, which will send the same data to different places. Right? A difference with the input also is that the output, you put all the, excuse me. Okay, I have to make a pause, sorry. Okay, sorry about that. Yes, so I was saying the data that we are going to send, we store it in the output. And there's a reason for that. So the data is created by the client, right? And so the client is going to write the data into the output. And remember, the data can be sent in multiple places. So if the output were not holding the data, we were just passing on kind of on the fly data from the client through the output to something else, and the other actor which gets the data use the reference where this data the data become a transient, and so it doesn't really exist anywhere because it originates from the client But the client at some point can decide to receive other input and modify this output or something like that. So by having a copy of it in the output guarantees that it will remain the same until you are ready to go through another cycle on it again, right? That's why there is a data here. And
is there any safety mechanism to check or assess if you are overwriting something in the copy of the data before transmitting the data?
There's no, you always, before sending the data with the output, this data variable is always overwritten by the client, client.
Before sending the data, it's yeah. Sorry, can you repeat? Yeah.
Yeah. Yes. Let's go to the send function. Like this, you can see a bit more the mechanism, and then we'll come back to the question. So here. So the first thing the send function does is to get a lock on the client. We're familiar with mutex, and then invoking the right function. Here you see the output. The output requires that C, which is the client type, implement the right trait. Again, make sure that we have the right functionalities to do that. So we write data from the client and we save it to the data properties of the output. And this is an arc, in fact, the data here. So we're going to, in fact, to send reference to the data held by the output. So this variable is overwritten by the client, but as long as there's no new data, it remains the same, and we just share reference with other actors. So you see at some point I invoked on the transmitter here, I invoked a send async, and I clone the data. But because the data is a arc, when you clone an arc, you don't copy the value in memory, you just get a new reference. Okay? So that's really what send doing, and if it's going to do that, it's an iterator because we have multiple sender, because we can have the same output connected to multiple other actors. So we iterate, we have an iterator through the vector of senders, and for each of them we invoked the send function, cloning the reference to the data which is held by this output.
So does cloning it make it so that it has a new reference so that you can't overwrite that, right?
Exactly. The actor will have a reference to that data, and the reference data is in an arc without a mutex here. So it can never mutate this variable. It's safe. It's in an arc. You get a reference to it, and you can only read it. You cannot change it. Okay. So if we go back to your original question, Rodrigo, does it answer it or not? I'm not sure.
I don't know if exactly. I don't know if I'm thinking the correct way to make the question. I basically, as always, I was thinking about our simulation framework, and I was thinking if there is any safety mechanism to avoid that we update the state of something in our simulation framework before using that data.
We can, but I think it's not. We can. So, but the sequence, remember, is like you get an input, you update your state, and you write the output, right? So and this output, effectively, you cycle back. So you could read, update, and then the data in the client, which correspond to the data in the output, could be different. But because we copy the data from the previous cycle in the output, then you don't overwrite it.
Okay.
That's why I created a new variable in output.
Another place.
Exactly. It's why I save the data in the output, because otherwise I could effectively not have that and only send a reference to the data in the client directly through the output and to the. But then that means that the other actor, which expect some data, when the cycle of this actor that has sent the data go back, it could modify. The client has the power to modify his own data, and that can. I have to put my hand back in this. That could change, but here it cannot because we have read, update, and output, which copy the client data to the output. So if the client changes state, this one doesn't remain until we invoke the new output. Okay, so you cannot do that. That's why I created this data here.
From the client standpoint, I understand. I mean, we don't have the risk of losing information, but depending on the way we connect the actors, there may be a chance of you updating, as you said, we take the data, we update the state, and then we output the information. But it's inside of an actor.
Yeah.
Imagine that you did not transmitted the data of that actor to another one. So you did not use the information outside there.
Mm-hmm.
And then because you made something wrong when you were connecting the actors, a new cycle of reading, updating, output goes on. So this means that, okay, you lose the information that you stored, but now you have two information inside of an actor. And this is because you made something wrong outside of the actor. That's my point. I don't know if I made my point clear.
Yes. Effectively, if you have an output and you forgot to send it, then the next cycle is going to be overwritten. But that's something you need to.
Yeah. Okay. Yes. Because in our framework, if we do everything correct, you should never overwrite an information. Everything that you produce inside an actor should be consumed.
Exactly. So if you have an output, it should go out. Otherwise, if there's a check that is done at some point, I will show you. If you create an output. No, sorry. I'm thinking about the scenario. Is okay. How can you? Well, it's really difficult to create an output without connecting it because you remember the process is add output and into input. So you really have to make an effort on you to make a mistake to not have that. Okay. But it could happen. It could happen. Yes. But yeah, that's this kind of obvious mistake. I leave them to the developer. I try to be safe on things which are a bit more difficult to find out. But adding an output, you will see without being followed by into input effectively, it won't be catch, I think. But you have an output, it gets not connected. Yeah, the program won't even crash. It may just hang because if you have an actor which expects some data and it's not connected, it just wait and it will block everything. So you will notice that way too. So I think so in that case, the system, you won't get something wrong. You just be waiting for a long time for your simulation because it will never stop. So you will notice at some point. I think it's what will happen. Okay?
Okay. You answered my question, yes.
Okay. So that's the output. So very similar to input in terms of the data you have here. There's I will explain later why we need Bootstrap. Except that we have a vector of senders and we copy the data here. It's for safety reason. or not overwriting everything to the client and the output. And one more thing I wanted to say, yes, the data that you expect from the client can be none if there's no data. And it's one way to terminate nicely the simulation. If you check if there's some data that is sent, you see the type here, arc of data. If nothing, then it will destroy the transmitter and return an error. And the error won't make your program crash. It's something you can do with Rust. You can catch error, and this error will be sent back to the actors, and the actor will notice, oh, we disconnected here. When you drop the transmitter, you disconnect. So he says, okay, I'm going to exit from my loop and close myself down. So you see, remember, I will show you that the actor has a loop that it's running. We can maybe see that next running. So when he catches this error, he says, okay, I have to stop because otherwise I don't have any connection. I lost my connection. And I close my loop and I close myself. And when he does that, all the other input and output are going to be required to also be dropped, so to be disconnected. And I will show you at some point that an input and output are made in pair. So if one is closed, the other one is made aware, and the other one is within another actor. So that generates the same type of error that we're seeing here. So again, this loop of this other actor is going to stop. All these input and output are going to be collapsed at some point. So their corresponding receiver or transmitter and other actor are going to see that, and in turn they're going to collapse. So like this, everything collapses, and the simulation stops. Nicely. So when you write the right implementation for an input to a simulation, you always have to think about implementing the case where we return none, because it's a way for you to stop a simulation. Okay. So input output, we saw that, and we'll probably come back to show you other aspects of that, but I think we saw the main feature, read, write, on the client for input and output, and send and receiving for the input and sending for the output with the locking mechanism of the client to make sure that we have a single access time. There's some extra things in the send of output. In fact, we send all the output in parallel to the multiple client. But that's a detail of implementation. I won't bother you with that from now. Okay. So you see how the input and output are defined. And then we can go back to the main program. Because, in fact, this input and output, I wanted to show you that, like, you have a feel how it's implemented, but you will never really need to access that directly. It's really hidden behind the scene. What you really need to do is use add output on an actor. Just like we're going to create a new output and create a builder, and then we build it, as I said. And it's where you really get access to, you create a new output. And as I said earlier, input and output are created in pair. So what you get at the output of this build function, it's an input that and then you need to assign it to another actor. In fact, here I must have changed that at some point. Why it doesn't want me to say? Okay, I would like to modify the code. Why? All right. Here I have two clients, in fact, that I want two actors, that I should have that multiplexed. So you see, I remember that the output, you can have a vector of output to connect to multiple, but you need to tell him how many of this client you're going to connect to. And here it's 2. So you pass the multiplex 2. So you're getting an output with a vector of sender, in fact. And one by one, you're listing the actors you're going to connect them to. That makes sense? So there's some safety here that are part of that model. The compiler will check for you that you have defined a read and a write function, so with the same data type. So the data type, we pass it here, F64 signal to filter, that's the data type of data. If so the source and the filter actor, or the source and the sync actor don't have the same data type defined for the read and write function, you will have a compiler error, right? I said last week that actors can have the same rate for all their input, the same rate for all their output, but input and output rate can be different. But when you connect them, the input rate, the output rate of the source must be the same as the input rate of either filter or sync. Otherwise, you have undefined behavior. The compiler checks that for you as well. Okay? We try to show how it's done now. Here you have I used to yeah, this is. So if we go to actor, add output. So this is the main function which creates a new output. And you see that it returns itself, in fact. And an actor output builder. If we look at this one, not too useful here. Let's go back. Let me think the best way to show you what I want here. Do we get an actor output build? Oh yes, no, it's here. I should. Where is that? Default. Where do we go? Actor output builder. Ah, yes, it's there. A bit it done. What I'm looking for, where is it? It's here, I think. Add output true. Enter. Add output. The one. Yes. Yes. Let's go through step by step to understand what's going on here. Let's go back. So let's see what the add output is doing. Again, actor, add output. So after the add output, we have our actor output builder, and we have a tuple, in fact. Let's see what I'm doing with the tuple here. I'm missing something. What am I missing? I'm missing an element. I'm lost. Just a minute. Here we go. That's a bit tricky to find your way. So add output. Let's annotate that for now. Add output. What you're getting here, it's a reference to the actor, and you get source and an output builder. Is what you're getting here. go back to those actors. Add output give you the actor output builder. Okay, so we have this type here. And I have a trait which is defined on that type, which is add output trait. See, it's implemented here on the foreign types. It's a bit hard to find sometimes. And it's implemented for, oops, yeah, a tuple. Yes, that is right, a tuple, which is effectively a reference to an actor and an actor output builder. Okay. So you get this type here, and we have different properties of an output that you can set. Multiplex, we saw when we say we're going to send this output to multiple place. I will come back on Bootstrap. Unbounded, the output, the channel have a buffer, and you can collect your the data you receive in a buffer and fill it up, and the receiver will read from that. Or you can just have a mailbox with a finite number of messages you can pass. Per default, you can put only one message, but you can have it unbounded. Anyway, so that's what this add output trait allow you to do on this tuple here. So you may wonder why do I apply a trait on a tuple? I could just have it would make more sense at the output of add output to have just the output builder. Why keeping the actor here? Okay, so let's see what happens when we do so when we build at the end, we still get a tuple. So we create the add output. We have this odd tuple here where we have the original actor and an output builder. And in fact, we just use the output builder to add some properties, to define some properties on the output. And when we build, we still output our original actor. And now we have the vector of receiver. So an output creates a vector of transmitter, and then the counterpart is a vector of receiver, right? So in that particular case, we'll have two of them. And that goes into the into input function. So let's look at into inputs. I hope this we can get clearer. Into input is like it's a function of another trait, which is implemented effectively for this tuple type of an actor and the vector of receiver, or we're going to make input. And this has only one input, which take as in one input, which take as input so this tuple and another actor, which is the input actor, right? So now we have really the type here. It's the output actor, the receiver of the input, and the input actor, right? So the reason why I kept the output actor to the chain here of call is because I want to make sure that both actors have matching types, right? So if an actor has input or output type may have different, different actor, different client, different type. But we want the output rate to match the input rate. So if you look at the definition here of the input and output rate for the output, for the client, which has the output, we have the NI is the input rate and and O is the output rate. And we implement that for another actors, which also define this generic type. And you see as another client that is input rate now, and O is matching the output rate of the original client. If I was not passing to this function, implementing this trait for this output actor, I would not be able to check that I would not be able to use the compiler to check that input and output rate are matching. So it's a bit convoluted, but it's really, really very useful. And it has saved my life several times. It's a bit dramatic, but it is true. Because it's very easy to mess up the input and output rate when you have, especially for applications we have multi-rate. And the compiler will tell you, okay, no, I was not expecting that. You cannot do that. Okay? So that's really how it is. Sorry, the dog is going to bother me until I do something to him. I can wait. It's funny, she's a bit scared to go down the stairs, so I don't have to carry her down, I just have to encourage her. Say, yes, go, 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 and then she goes. Okay. Otherwise, she's going to bark and bother me. Just in a corner. So you see, she's back. Oh, you're back. How are you? Oh, I lost them. Okay. Anyway, what I was saying. Yes, so you see a bit the mechanism I have to use to ensure safety among that. And even the type here, TU, are the same among the different input and output. Okay, so that's a this little call here is very, very safe. In fact, it will catch up a lot of error we can make with that. I wanted to. I'm running out of time, so I'm going to stop here. I hope it's not too boring, all these things here. But that's for the input and output today. I will stop recording.